We've spent the last week defining terms, position, distance, displacement, vector, scalar, and using those terms to calculate speed and velocity in word problems. Today what we're going to do is describe speed and velocity and position and distance and displacement, not with word problems, but rather graphically. So we're going to use pictures instead of words to describe what's going on. We're going to plot, or we're going to interpret, I should say. Tomorrow when we do our lab activity, we're going to plot. Today we're going to interpret position time graphs. Now, before I start, I want to let you in on a couple of things here. Okay? Whether we're talking about position time graphs or velocity time graphs or any other graphs. When you see the title of a graph, always remember this. The first word in the title is always the y-axis of that graph. So you know right now, before you even see these pictures, that these graphs are going to have position on the y-axis. That's this axis. The second word in the title, whether it's called position time or position versus time, the second word in the title is always going to be the one that appears on the x-axis. That's this one. You guys remember what a manipulated variable is? Well, a variable that can change. Let's be more specific, though. It's usually a variable that the experimenter changes, right? The responding variable is what responds to that. How many manipulated variables can you have in a single experiment? One. How many responding variables can you have in a single experiment? One. And control variables, those are the ones that stay the same. You can have thousands of control variables, although we don't usually list thousands. You can have thousands or even millions, theoretically, of control variables, an infinite number of them. Control variables we don't plot on graphs because they stay the same, but manipulated variable and responding variable we do. The manipulated variable will always be on the x-axis, and therefore it will always come second in the title. The responding variable will always be on the y-axis and will therefore always come first in the title. So position versus time would be the same as saying y versus x, or it would be the same as saying responding versus manipulated variable. Make sense? I want to go through some shapes of graphs with you first, and then we'll go through some number crunching for those graphs. 5 different shapes of position time graphs. In all 5 of these cases, time would be our manipulated variable and position would be a responding variable. That seems a little bit kind of weird sometimes. Time is your manipulated variable. We don't change the time, do we? Tomorrow's experiment is going to involve putting masking tape on the floor at 1 meter intervals. So 0 meters, 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, and so on. And then you're going to set a little motorized car in motion at a constant velocity, and you're going to basically time where it is at various points. Okay? What are you manipulating here? So a lot of people look at this and say, oh, we're manipulating the position, right? Because that's what we're looking at position 1 meter, 2 meter, 3 meters, and so on, right? We're manipulating the position. We're not. Okay, we're manipulating the time. Where the object is responds to how long it's been moving for. Does that make sense? Where it is, it's where it is because of how long it's been moving for. So time would be our manipulated variable and position would be our responding variable. Therefore, time is on the x-axis and position is on the y-axis. Let's take a look at each of these shapes. I'm going to give you a word of caution before we go through what each of these mean. That word of caution is this. Don't memorize what we're about to write down. Understand it. Think about each graph. Interpret each graph. Don't memorize each graph. There's 5 shapes here. If you see them on a test, each one of these 5 shapes on a test, and you memorize it, you'll get it right. But what if we see something on a test that's a little bit different than what you see up on the board right now? And I'll give you an example in a minute of something that maybe could appear on a test that isn't on the board right now. We want to be able to deal with that using skills that we're learning as opposed to memorization. Okay, let's look at this one. Tell me what's happening there. Position time graph, the object is described by that straight line, but sloping upward. Sebastian, what's going on there? Acceleration, so speeding up. Okay, let's look at that for a second. If we look at a time interval here, okay, that's a pretty small time interval there, right? My displacement, which is my change in position, is also pretty small. Agree? Let's look at a time interval up here. Looks like about the same time interval there, right? Let's look at my displacement. Looks like about the same displacement as I had before. So if in the same amount of time I'm covering the same distance, am I speeding up? No. If in the same amount of time I'm covering the same distance, then I'm going at a constant, we say constant velocity because we're talking about position time, right? If it was distance time, we'd say constant speed. I wouldn't mark that wrong on a test probably, but constant velocity technically. See what I'm saying about thinking about it as opposed to memorizing? Okay? Understand the reasoning that I just used so that you can figure that out sometime. How about that second one? Position versus time. This is also a straight line, but it's a flat straight line. Yep. Yeah, so stopped, right? Look at the position right here. Again, don't memorize that. Look, figure it out. The position right here is whatever. The position right here is the same. The position right here is the same, so it's stopped. It's not moving. I don't care exactly how you write it. Stopped, not moving, velocity of 0. Any of those things mean the same thing. What about the third graph? Yeah. Oh, good, excellent. Well, let's say a constant negative velocity. And what we mean by that is backwards works, but be careful. It doesn't mean necessarily say a car is driving in reverse, right? It means the car is going in the negative direction. So car drives to Calgary, it's a constant velocity. I mean, assuming it's not speeding up or slowing down, a constant positive velocity. Car drives back from Calgary, it's a constant negative velocity. It doesn't have to be driving back from Calgary in reverse. You don't have to be walking to the front of the room and then walking to the back of the room backwards. You just need to be moving in the backwards direction, the opposite direction. Make sense? Constant velocity, but negative. Well, if we're going to define that as constant negative velocity, we really should define this one as constant positive velocity. Fourth one. Sebastian. Yeah, this one's acceleration. Let's take a look, Sebastian, at the same reasoning we used for the first one. We have a time interval here of, I don't know, whatever that time is. We have a certain displacement here, which is pretty small, right? It hasn't gone very far in that time interval. But if we look up here in a time interval that's about the same, look at the displacement, it's covered quite a bit more distance, right? So it's covered more distance in the same amount of time, which means it's got to be speeding up. We're going to say that's a positive acceleration. Actually, let's just say acceleration. And then let's say in brackets, it's positive. In other words, it's speeding up. It's a quiz or a test. You write down positive acceleration, it's correct. You write down speeding up, that's correct as well, right? The last one here, 7. Yeah, this one's deceleration. It's a negative acceleration. Let's look at that reasoning again. During a certain time interval, well, it covers about that much displacement. Same time interval up here, it covers hardly nothing, right? Much smaller distance or displacement. It must be slowing down. All right. Let me give you another one here. Okay, that maybe could appear on a test. Okay. Here's position versus time. So again, think about it. I mean, if this appears on a test after we go over it today, great. You can have it memorized, whatever. But the point that I want to make is that sometimes we see something on a test that looks slightly different, but we have to use our reasoning skills to figure out what it means. Let's use our reasoning skills to figure out what this means. Okay, Isaiah, what did you say? Okay, but what's its motion? Okay, you're right. It does. Yeah, constant velocity, constant negative velocity. It's still constant negative velocity, right? Just like diagram number 3 was right there, constant negative velocity. But understand the meaning of that constant negative velocity in this case. Okay, let's say the 0 point is Isaiah. Okay, I'm up here. I might be walking backwards. I might be just walking forwards, but towards him. Okay? I'm walking in the negative direction now. My position is getting smaller and smaller and smaller and smaller and smaller. What's my position right now? 0. But I keep walking. Now my position is getting bigger, but negative. It's getting to be a bigger number, but negative. Any way you look at it, it's still a constant negative velocity. Whether we're talking about going towards him or away from him, it's still a constant negative velocity. Simon? Nope. Nope, it doesn't represent a change in direction. If you had, we'll talk about this in a little while here, not today. If you had a velocity time graph and you did this, then that would represent a change in direction. And think about that. You'd be slowing down, slowing down, slowing down, slowing down, 0 velocity, stopping, speeding up in the negative direction. That would be a change in direction, right? Okay, this one's not. We'll talk more about stuff like that when we get to velocity time graphs. Good. Okay, what about this one? This one's kind of a neat one. Once again, position versus time. Hey, what's our manipulated variable here if we look at this graph? Jack? Time. How do you know? It's on the x-axis. If I was to title this, I would title it position time or position versus time, because position is on the y-axis, our responding variable on the y-axis. Okay, here's our graph. What's going on there? Max? Okay, so it's not possible, right? No, it's a trick question. Right? The object is moving from one place to another instantly, without any time going by. It's like it found a wormhole, and it went from here to there, but no time has gone by. Right? So it's not really possible. Let's try another one. Oh, I like this one. What's a responding variable on this graph? Position. It's on the y-axis, right? Our title would be position time again, position versus time. Explain that one for me, please. Again, this is not something that we can have memorized because we haven't seen this, but let's think about it. Good, good. It's not possible because time can't go backwards. Look, here you're going at a constant velocity. Constant velocity, constant velocity, constant velocity. You reach a certain time, and then what happens? You jump in your time machine, and time starts going backwards, and you start going offline, I guess, too. Time starts going backwards, and you keep moving. That's not possible, at least as far as we know, it's not possible, unless one of you is from the future and just isn't telling us. Then, as far as we know, that's not possible, right? So another trick question. I won't give you one of the tricks on a test. I might give you something like this. Okay, that's fair game. But I won't give you a trick like this that's not possible on a test. The only reason I gave you those two ones that are possible was to illustrate, again, the reasoning that we go through to figure out these things, that we don't memorize them, that we think about them. All right. Let's start dealing with graphs in terms of numbers. Yeah, you're not going to see any numbers on the board here right now, but it's going to lead us. What I'm going to show you is going to lead us to that. Here's our graph. It's position versus time. Time is our manipulated variable. Position is our responding variable. Now, a graph is a straight line. Notice it doesn't go through the origin. Is that okay? Sure it is. Sure it is. Some graphs don't go through the origin. Some do, some don't. It's okay. Not a big deal. It's a straight line. What does that mean? Constant positive velocity. Even though it doesn't go through the origin, does it still mean the same thing? Sure it does. It's the shape that matters there, right? Have you guys ever seen the equation in math class, y equals mx plus b? How many people have seen and used y equals mx plus b? Okay. Just about everybody raised their hand. I think everybody has seen it. Not necessarily everybody remembers seeing it. What does y equals mx plus b describe for us? Or for anybody, for that matter? Cameron? Okay, so it has to do with the slope of the graph. B is a y-axis or y-intercept. Yeah. 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 Yeah, it is. Yeah. Okay, so you're saying it describes a few different things about the graph. So it describes the graph. It describes a very specific graph, though, and that is a straight line graph, right? Y equals mx plus b is the equation, the general form of the equation that describes every straight line graph. If you had a curved graph, it wouldn't. If you had a graph that looks like this, and we won't deal with this for a while, but y equals mx plus b would not describe that. Everybody know what equation would describe that one? That's right. Yeah, it's not constant. So you can't say y equals mx plus b. What shape is that? Remember that? Parabola? Okay. But don't worry about that right now. Right now, please recognize that this equation, because it's a straight line, can be described by this equation, y equals mx plus b. Every straight line graph, including this one, can be described by that equation. Now what I want to do is tailor this equation to this specific graph. In other words, I don't want it to be so general. Y equals mx plus b. I want to change this to the y variable. I want to change it to position because that's what's on my y-axis, right? Position. I'm going to actually make it the final position. I'm going to write the word slope in. Replace m with slope, the word slope, because in time, when we do problems involving mass, I don't want to start getting mixed up between mass and slope. What's my x-axis? Time. So let's replace x with time plus b. So now I've got an equation that describes my graph that's really y equals mx plus b. Looks a little bit different because I've substituted variables in for y and m and x. D is equal to the slope times t plus b. Where does this lead us? Well, nowhere yet. Now what I want you to do is find an equation on your data sheet. It shouldn't be too hard to find it because we've only done one. Find an equation on our data sheet that has the same variables in it. Maybe it has more in it, but it has at least distance or position, displacement, time, whatever, d and t. Do we have an equation with d and t in it? What is it? VIT plus 1/2 AT squared? Okay, that's not going to work. You know why? Because this is d and t. That one's d and t squared. Make sense? Do we have an equation with d and t? Don't look too hard for this. V equals d over t. That's d and t. Now we're going to rearrange that to solve for d. Oops. We're going to rearrange it to solve for d. I take the t up by multiplying both sides. In fact, I'm going to actually change this a little bit and say delta d is df minus di. Is that okay? That's the same thing? And then I'm going to just rearrange it a little bit to get df by itself because that's what's by itself in the blue equation here. df is equal to v times t. How do we get rid of the di? Subtracted. We added on both sides. Now, look at the blue equation, look at the green equation. df is equal to the slope times t plus b. df is equal to v times t plus di. Cross off df, because it's in both of them. Cross off t, because it's in both of them. What are we left with? Slope times t, slope times t. The slope of this graph represents the velocity. Plus b, plus the y-intercept, plus the y-intercept. The y-intercept will be equal to the initial position. Now, you may have done this in Science 10, not the technique that we just did. You may have just learned that the slope of a position time graph is velocity. But now we know how to figure out what the slope of a graph means. We're not going to have to do this all that much in Physics 20, but in Physics 30, you're going to have to do this a lot. In fact, you will get a question on your diploma exam. It'll be worth 2% of your diploma exam. They'll give you a graph that you have never seen before in your life. And you'll have to figure it out. And you'll figure it out, I'm telling you right now, you're going to figure it out using the technique that we just used. Figure out what the slope means, and then use it to determine what you need to find. If this made sense to you, great. Don't worry about being able to do it yourself yet, as long as it made sense what we did. We'll do a few more examples of this through Physics 20, and then we'll do lots of it in Physics 30. Right now, I want you to remember this. The slope of a position time graph is equal to the velocity. I think reasoning, logic would tell you that the y-intercept would be the initial position, right? Where it goes right here, that's where it starts, right? Slope is equal to velocity. That's the big takeaway from this. All right. What else can we find from this position time graph? What else? Now let's label it. Let's draw the same picture as we had before, right here. We can find the position on a position time graph. What's the position at this moment in time? How would we find it? I'll give you a hint, it's easy. Just go up and over, up and over. This would be the position at this time. Up and over. The displacement on a position time graph, what's displacement defined as? Quinn, what's displacement defined as? Can you help me with that? Good, it's the change in position. If we know how to find the position, then we should be able to find a change in position, right? Position is up and over. You want to find displacement? Go up and over twice. And then subtract them. Let's say the displacement is df minus di, the final position minus the initial position, which is really just up and over twice, then subtract. Up and over, subtract the two. That gives you displacement. Velocity, the average velocity on a position time graph. We just learned that, didn't we? It's the slope of the graph. You guys remember how to find the slope of a graph? You guys remember the equation for slope? Yeah, okay. Some people say rise over run. Right? You heard that before? Rise over run. Some people say y2 minus y1 over x2 minus x1. Have you heard that? Some people say delta y over delta x. Simon just said delta y over delta x. So let's write that down. Oh, but wait a second. We already know what average velocity is before today. Average velocity can always be found by using v is equal to, before today, delta d over delta t, displacement over time. Look at this. You might not get as excited about something like this as I do, but this is elegant. Look, the slope is delta y over delta x, right? And we established a minute ago that the slope of the graph is equal to velocity, right? We already knew that velocity was delta d over delta t. So it's either one of those, right? Delta y on this graph, y2 minus y1, is that not displacement? What's delta x on this graph? x2 minus x1, is that not delta t? So isn't delta y over delta x the slope of the graph? Isn't that exactly the same thing as delta d over delta t? Isn't that what we've already been doing? Sure it is. Do whichever way you want. I don't care. Think of it as rise over run, delta y over delta x. Think of it as delta d over delta t. I don't care. It's the same thing. And the instantaneous velocity, that means the velocity at one specific moment in time. If you have a straight line graph like we do here, it's going to be the same as the average. Now, if it's not a straight line, or direction changes, or something happens, then it's not the same thing. We'll deal with that later on. If it's a straight line, and it will be for you for now, then it's the same as the average velocity. Think about that. If the average velocity was 5 meters per second over this interval here, and it's a constant velocity, then it's got to be 5 everywhere along that line, right? You can't have a constant velocity of 5, but yet have the velocity of be 7 somewhere along the line. Can't happen. So all you got to do is find the average using the slope or delta d over delta t, and then say instantaneous is the same thing. Okay, I want to do an example. In the example, the good news is this is in your on your worksheet. So I think it's the third worksheet, the fourth worksheet. It looks like this anyways. Single question on one page. I want to go through this, and then we'll set you free to work on some questions on the back side of that. What's the position of the object in the graph to the left at 10 seconds? Up and over. Looks like it's 30 meters. Positive 30 meters, whatever that means, to the north, to the east, whatever. It's positive direction. The displacement between 0 and 10 seconds. The displacement between 0 and 10, that's final minus initial, right? Position. My final position is 30. My initial position at 0 seconds is 80. So my change in position, or my displacement, would be negative 50 meters. Don't say negative 50 to the south. Okay, don't say 50. It's negative 50. Or you could say 50 to the west. Actually, we do know which direction it is, right? It's the negative direction, which is to the west. Don't say negative 50 west. Say negative 50 or say 50 west. Either one of those works. It's the average velocity of the object between 0 and 10 seconds. Well, velocity can be the slope, delta y over delta x, or it can be displacement divided by time. And since we already found the displacement, let's just use that. What do we know about the object in this graph? It's going at a constant velocity. Yeah, constant negative velocity. So if that constant velocity is 5, what's the instantaneous velocity at 2 seconds? Negative 5. What's the instantaneous velocity at 7 seconds? Negative 5. The velocity is the same everywhere, right? All right, if you're okay about that, let's try the back side of that worksheet, starting with question number 1. Okay, let's take a look at number 1 to make sure everyone's on the right track here. Number 1A says, what's the position at 7 seconds? What do we do? What do we do? This is the easy one, right? Up and over, right? At 7 seconds, we're going to go up and over, and my position is 30 meters. 30 meters to the north, to the east, positive 30, whatever that means. All right, next one, displacement between 0 and 5. The displacement is the final position minus the initial position. The final position at 5 seconds is 30 meters. And at 0 seconds, it's 0 meters. So we're going to say 30 minus 0 is 30 meters again. The average velocity between 0 and 5. Well, we can think of velocity in a couple of different ways. We can think of it as delta d over delta t. Or we can think of it as delta y over delta x, the slope. Either way works. They're both correct. Delta d here, we already figured out, is 30 meters. The displacement is 30 meters. The time is 5 seconds. So that's going to give me 6 meters per second. Oh, this one's interesting. The average velocity between 0 and 9 seconds. Between 0 and 9. What's interesting about this one? What makes this one kind of a little bit different? Yeah. Yeah, it stops. Like we got something happening, constant velocity, and then all of a sudden it stopped. So two different things happening. Here we can't use the slope because it's not a straight line. Right? Here we've got to use displacement divided by time. The same method we used for question C. The displacement here between 0 and 9 seconds is 30 meters. Time is 9 seconds. 30 divided by 9 is 3. Or 3. Thank you. What's the instantaneous velocity at 3 seconds? Same as C, because it was a constant velocity up until 5 seconds. So it's going to be 6 meters per second. Oh, and this is the one that gives people trouble all the time. What's the instantaneous velocity at 8 seconds? Is it 3.33? No. What is it? 0. It stopped, right? Again, that's used in our head, right? Thinking about things rather than memorizing things. 0 meters per second because it stopped. All right. Keep going with question 2, 3, and 4. Your homework tonight will be those 3 questions if you don't finish them in the next 7 minutes of class.